Okay, should be recording.
Hello, hello.
Hello.
Yeah, we still have 1 minute. Oh. Okay, let's begin. Yeah, I'd like to draw your attention to a few reminders quickly. Let me bring up my mask here. Yeah, so please sign the signature sheet after you collaborated and each contributed maybe 2 or 3 points that you learned during the lectures. Okay, and then sign after 2:40 p.m. Remember to give me the timeout sign. And you can also write critical thinking question on the sheet if you have any questions. Okay, I have posted the extra lectures for meeting 7 and meeting 11. So meeting 7 is before this meeting. This is meeting 10, and meeting 7 extra is before, and meeting 11 is after this one. So please look at the extra meetings, because these are like for reviewing the single degree freedom system or the scalar linear second order ODEs. Okay. And so here are some measures that I took to develop good communication of ideas and facilitation of learning. Continuous anonymous feedback. You can provide me feedback anonymously anytime. So if you have any idea to improve, please let me know. And fill in the survey of note-taking methods so that I can continue to provide certain surveys. So right now we have 42 respondents out of 51 students, so we need 9 more students. If you have not filled out this form, please do so, just 2 clicks. Weekly schedule, you can see the weekly schedule in this document, or also the weekly schedule in the content. In the weekly schedule in this link here, I have also the sections and also some references if you need to read more. Okay, like books and things like that. This list of topics here can serve as the reverse way to find my lecture notes. For example, in the daily lecture summary, you can see the my lecture notes and then the contents of my lecture notes, right, as I do in each lecture. But later on, suppose that you need to say, oh, I need to review generalized eigenvalue problem. You can go to this list of topics, do a search, and I showed you how to do a search with different web browsers, right? The best method is to click into the document and do Control F, then you can find. So that way, if you have a topic that you need to search, this is the best place. And then once you find the topic, then you can see the corresponding lecture notes. Okay, so for some reason, I had this last semester, but many students did not know how to use or take advantage of this this service. Okay. And I have already updated the active learning credits for with team members, particularly for meetings 1 to 3. That's before team formation, so you may want to go and check. Be sure that your name and team numbers will be correct. For example, there were 2 Kevins and 2 2 people with the same first name, so you may want to double check. Okay, so here is my handwritten notes from last time where I started to coach you how to solve exam problems. This is the actual exam from last semester. So essentially I was coaching the class of how to do that. And this is also a good way to be motivated to learn because it's in the exam. And so in the same spirit, let me proceed. Regarding this parallel spring and springs in series, many students may memorize the formula, but the goal is not memorization. Okay, the goal is derivation. Know why you have certain formula. That's really the goal, and that is stressed here. Okay, and so we have done all of that. So we essentially replace the continuous bar in element 5 by a spring and 2 continuous bars in series by an equivalent spring, right? First, each continuous bar by an equivalent spring, and then 2 springs in parallel by yet another equivalent spring, right? And so a couple of things that I'd like to work with the class today. And the first thing is why? And nobody asked. This is a while ago. This is, remember when I was referring to the Akashi-Kaikyo bridge and the continuous bar? Why is the, yeah. Why is the spring that is equivalent to a continuous bar with Young's modulus E, cross-section area A, and length L is written like this, K equal to EA over L? Any contribution? So let me start. Give you a hint. I think of a cantilever beam. And let me move this down. This is the result, right? And so on the left end, it would be clamped, and on the right end, and we'll consider only axial deformation, right, along the length of the beam, and think of and apply force F here, and the properties of the elastic bar here would be Young's modulus, area of cross section, and L. And let me bring in our classmates here. Yes.
Because it shows the deformation of the spring.
Because it shows the deformation of the spring. So essentially, we want to derive this expression. We want to show this expression. Okay. I have already explained the physical meaning, the physical field for this expression, meaning that the spring constant would be larger if you have a stiffer material, meaning higher Young's modulus, or a larger cross section. On the other hand, it's inversely proportional to the length. The longer the bar, the weaker the spring constant. But that's a physical field, you know. How does one come up with this formula? So what is your team number?
Team 7.
Team 7. And the name?
Nick.
Nick, okay. So the name. Yeah, and I'd like also to move forward after. So one more, okay, and then we need to move forward, and this is meeting 10. Yes, the man. Oh, Kevin, sorry, Kevin, team 6.
You can drive it using Hooke's law.
Hooke's law? Excellent. Excellent keyword. So Kevin, how do you write Hooke's law?
Stress is equal to
Yeah, stress sigma equal to Young's modulus times
Strain.
strain, right? So what is stress equal to? Normal stress is
Force over
force divided by area, right? And what is strain?
change in length over length.
Increment, sorry,
Change in length over
change in length
over original length.
divided by length, right? And you can think of change in length as d, or displacement at the tip of the bar. Okay. And so with this, you can deduce that F is equal to E A divided by L times D, right? And F equal to KD, right, is the mantra that we often cite. And so this is K, this is the equivalent spring constant. That's it, the formula has been rigorously derived from mechanics materials. Okay, so it's no longer a need for memorization. All right, and you see the derivation is simple, it's fundamental, and that's the kind of learning you want to have or to emulate rather than memorization. Okay, next question. Next critical thinking question. Is that all we can do? You know, first remember we replace the continuous bar by this equivalent spring. We replace two continuous bars in series by an equivalent spring, right? Is there anything else that we can do further to reduce the problem? Let me pick up a new. I hesitate between the van and. Did you contribute before?
Yeah, way long ago.
Okay, so what's your name?
Kenny.
Kenny, yeah, I remember I did mention about Kenny G, right, the saxophonist. Okay. Okay, Divine, please, next time.
I was
Right?
gonna
So
say,
let Kenny.
you could say that the springs with the constant K2 and K4 are in a parallel.
Very good. These two are in parallel. Combine them together. That's it. Reduce the system even further. Let's see. If I forget someone, because in the heat of the action, I may forget to note down. So please feel free to remind me after you check. Okay. So Kenny is team what?
8.
Team 8. Team 8. And then there was someone else. I think Kevin, yes. Team 8. Kenny, okay. And Kevin is team 6. Because there are 2 Kevins, I remember now. I slowly get to know all of your names. All right, so let me transfer this figure to my new notes here. So let me open the old notes of meeting 9. Okay, so I can just copy this figure. And let me put it here just as a reminder. And I also put the same down here as Kenny said. Now we can get rid of this bar, right? And combine together with K2. So we X this out, remove this, and instead of K2, let's call it K2 bar, something different, okay? Such that K2 bar is equal to K2 plus K4. That's it. All right, so now we almost get the equation of motion. So the equation of motion is the same as what you saw for the three elements in series, right? The three elements, and each element is a spring and a damper in parallel. And now you just have, instead of K2, you just have K2 bar, so that's really no different. But you have the spring K5 that span from the right support to the mass M1, okay? So, so what would be, and the mass, let's recall the mass would be M1, M2, okay? So what would be the mass matrix? And recall that the equation of motion is M, D, double prime, and remember the underbar means a bold face letter when you type sec, and that represents a matrix quantity, plus C, D prime, matrix of the velocity. So M is a mass matrix. Whenever I say matrix, you immediately think, if I write by hand, that would be with the underbar, and if I type, that would be a bold face letter, right? And then D double prime is the matrix of the acceleration, plus the matrix, the damping matrix, times the matrix of the velocities, and times the stiffness matrix K, times the matrix of the displacement, equal to the matrix of the applied forces, which can be time dependent, right? So let's do attack one by one here. Mass matrix, anyone? How is the mass matrix written in this case? Yes, please.
M1 in the top left-hand corner,
M1,
in the top left, and then 0, and then
M1 0 and 0,
M2,
M2. What is your team number?
6,
Team 6?
3.
Team 3. You don't remember your team number, team 3, and what's the name?
Richard.
Let's see. Yeah, usually I need to. So, team 3 and Richard.
Yeah.
Okay. All right. So, like Richard said, you know, everything is the same and the mass didn't change, right? So you have M1, 0, 0, M2. So while I write it down, why don't you think about the damping matrix? Well, let's think about the stiffness matrix. Oh, okay, that's fine. The damping matrix next. Okay, while I write this down. And the reason I do this is that so that the shape of the letters look identically the same, you know. So that way you can recognize much easier. Okay, so damping matrix, anyone? What would be the damping matrix? Feel free to open the notes, okay? Feel free to look up.
C1 plus C2 in the top left,
Okay, Kevin, this is team
7.
7. Okay, so Kevin said C1 plus C2. Yeah, let me give the name of the C1 here, C2, and then C3. Right, so you have C1 plus C2. Remember, like I explained last time, you know, the mass M1 is between C1 and C2. So the coefficient that corresponds to the displacement of the mass M1, which is here, this D1, D2, would be the sum of these two, right? What next, Kevin?
My negative C2 in the top right.
Okay, so let's take care of the diagonal first, right? So what would be?
C2 plus C3.
Right, C2 plus C3. And then we take care of the off diagonal terms. That would be
Negative C2 for both of them.
minus C2 and minus C2. Okay. And the thinking is that mass M2 is between C2 and C3. So the term that corresponds to the degree of freedom D2 will be the sum of C2 and C3. And then, you know, the off-diagonal terms, which is essentially the coupling terms between D1 and D2, because the first equation corresponds to the equation of D1, the displacement D1. But it involves the displacement or the velocity D2. So this is called these two terms are called the coupling terms. And so, you know, C2 is between D1 and D2, and therefore you have the coupling term is minus. Don't forget the minus sign. Okay. So now the stiffness matrix. And Kevin, do remind me, okay, of your contribution. So stiffness matrix, someone? Okay, let's start with the stiffness matrix without element 5, you know, without the extra spring there. This is easy, right? You can, anyone? You can just follow the damping matrix, right? That will be K1 plus K2.
K bar 2. It's K bar 2 in this case,
Yes,
right?
that's right. K bar 2. And then down here you have K2 bar, because that's the new spring, plus K3, right? K2 bar, let's recall here. Yeah, you know, there's a bar here that you, okay. So it's a new spring called K2 bar, right? So for the displacement D1, you sum K1 and K2 bar. So that's the first diagonal term, very similar to this one. And for the second degree freedom, that's between K2 bar and K3, similar to this term. That would be K2 bar plus plus K3. Okay. How about the off-diagonal? How about the off-diagonal terms? Anyone? Come on, get active learning credit. Let's go back to the picture again. Right, except the off-diagonal coefficients is the coefficient that couple the degree of freedom D1 and D2, and anything in between that would go to the off-diagonal coefficient. So in this case, that would be. I'm sorry, I need to remember your name, Matt. Is it Matt?
Yes.
Yeah, teammate.
Teammate, yeah.
Yes. Okay, Matt.
It would be negative K2 for.
Yeah, that will be minus K2
K bar.
bar. Yeah, don't forget that. Okay, that's it. That's the solution of the exam. And to emphasize, let me put the minus sign in red. Okay, that's it. All right, divide and conquer. Simplify, simplify, simplify until everything becomes simple. Just a matter of, I prefer that you can re-derive rather than applying formulas. Yes, Kevin.
So for that extra spring, or are you about to do that?
Sorry?
The extra spring?
Oh, the extra springs.
Yeah.
Yeah, sorry. Yeah. So how do you deal with the extra spring? You know, this extra spring K5 here.
You have another spring term inside the force
Where
equation.
would you add that?
After the KD, I'd make a whole new matrix, I guess.
After the KD?
Well, you got the one KD with that matrix you just made, and then I'd make another one.
Another
just
one.
for the
Yeah,
for the spring by
okay.
itself.
You know, what's the method? The method is free body diagram, right? You need to isolate the mass, and now when you isolate the mass, you have the internal force coming from this spring here. Okay, so in addition to the internal forces coming from element 1 and coming from element 2, okay, and then the double bear force and the applied force. I'll let you work that out, but in the end, this is the so-called street fighting method. Street fighting method is actually the name of a book and the name of a massive online course from MIT X. Okay, I'll put the link for you. It's a serious course. It's not easy. Okay, it's called Street Fighting Mathematics. What does it mean? It means that you use physical intuition to feel the solution rather than going through the formal mathematical derivation. So the formal method is do free body diagram, do balance of forces, and come up with the result. Here is the street fighting method. Okay, so let's go back to the figure. Maybe I can zoom out so that you can see both. Okay. You see, this spring K5 connects the displacement D1 to the wall. Now the wall, you can think of it, is a boundary condition that you eliminate. That's A, B, C, D. That's the displacement of node D. That's equal to 0. So the stiffness K5 is added to the stiffness at the mass M1. Think of this. Think K1. K1 is added here. Okay? You have D1 and D2, right? The displacement D1, displacement D2. So you see that on either side of the mass M1, you have K1 and K2 bar. And now, in addition, you have K5. That is added stiffness to the mass. So the street fighting method is that here you need to add K5 right here. Okay. Now on the other end, it's equal to 0. The displacement at the support of the spring K5 does not play any role. It does not connect to any of the free displacement D1 or D2. So therefore, the only place is right here. Okay, so let me note down here. This would be where you put plus K5. All right. And move out so that okay. And so please derive this using free body diagram. Okay. But that's the result with the intuitive explanation. Okay. So please, it's important to keep this in mind. So now let me go back to the plan. And the plan is I'd like to, so all of this, I finish all of this, right? Further simplification, stiffness matrix, damping matrix, mass matrix. Actually, we did the reverse order, and then matrix equation of motion, right? That's the complete solution of problem 1 in exam 1.1. Okay, let's open up section 53C. Yeah, so the continuation is, let me do a quick review to refresh your mind where we are, where we were. Okay, that's the table contents, and over here we went through all of these. This is the example, right? A very particular example with numerical values for all of the components, springs and dampers. And the reason that it looks complicated, as I mentioned to you, because I solved the inverse problem. So that when you get to the model equation, when we uncouple later down the line, you would see that you would get very simple uncoupled scalar equation, right? And so this is the matrix equation of motion that we just reviewed for the exam problem. And these are just the matrices, the mass matrix, damping matrix, and stiffness matrix, just obtained by replacing the numerical values, right, of the springs and the dampers and the masses together. Okay, and so this, at this stage here, I think we were somewhere here. So now at this stage, this is a recapitulation of the matrix equation of motion in compact form. In compact form meaning that with the variable, matrix variables, and then this is in fully expanded form. Okay, so let me zoom in. All right. So here is you have we have reviewed all that. So now that's the compact matrix form with matrix variable, and this is the fully expanded form. This is also matrix form, but in fully expanded form, where you have the mass matrix, the matrix of the acceleration, the damping matrix, the matrix of the velocity, the stiffness matrix, the matrix of the displacement, and the forcing matrix, matrix of the forces, right? And h of t is a free time-dependent function where you can prescribe any function, right? Sine, cosine, logarithm, exponential, and that depends on the data of the problem. Okay, and so zoom out for the big picture, and then we zoom back in. So, and the next step is, I remember it was the contribution from Matt of Team 8. You have four initial conditions. You have 2 initial displacements and 2 initial velocities. 2 because this is a matrix with 2 coefficients. So each of these coefficients is an initial condition, right? And this is the initial condition involving the displacement. So d1, 0, meaning d1 at time 0 is 1 over square root of 5 times 1, right? d2, 0 is 1 over square root of 5 times square root of 6, or square root of 6 divided by square root of 5. Similarly, you have here initial velocity, right? Velocity of mass 1 at time 0 and velocity of mass 2 at time 0. Okay? Right? Square root of 3 over 10 times this column matrix, 1, and then the second coefficient is minus 4 over square root of 6. And you will see the magic of these numbers as we move along. And now one very important remark is that it turns out that the value that I selected for the damping coefficients for the third damper is negative. So what does it mean, a negative damping coefficient? A positive damping coefficient is a damping coefficient that dissipate energy, right? When you, for a single degree of freedom, when you let it undergo free vibration meaning without any applied forces, then the amplitude would decrease, right? Would decrease as time goes to infinity, because the positive damping coefficient dissipate energy. Now, negative damping is when energy is pumped into the system. So you expect the amplitude actually increases, okay, to infinity as time goes to infinity. And this has a very important application actually. This negative damping is the explanation for the collapse. For the collapse of the Takuma Narrows Bridge, okay, it's due to the self-exciting aerodynamic effect that when you derive the equation, you have the negative damping term. And negative damping, you know, reinforce the oscillation amplitude, and the amplitude of oscillation increases up to a point where the bridge will break. That's to keep in mind. And this is a problem that you already look at. So the next step here, this is the first step in the solution of the equation of motion, of the matrix equation of motion. Remember the matrix equation of motion that you saw? Quickly review several times from solving the exam problems to the current lecture notes. It represents two coupled linear second order ODEs, right? Coupled meaning that you cannot solve each equation separately, because in the first equation for D1, for the first displacement, you have D2. And in the second equation for D2, you have the presence of D1. And the coupling between equation 1 and equation 2 is represented, like I said, by the off. You have the diagonal of the matrix, and the off diagonal coefficients is the representation of the coupling. Right? Okay, so the first step to solve or to uncouple these two equations is to solve the undamped free vibration. What does it mean, undamped free vibration? Let's listen. Let's analyze the word. Undamped meaning no damping, right? So you see that there's no damping force. C times D prime, right? No damping force. Throw that out. No forcing function. No applied force. So the applied force is 0. Okay. So this equation is called the undamped free vibration equation, and this is the fully expanded form, right? That you have the mass matrix, the matrix of the acceleration, the stiffness matrix. Maybe let me use this here, the stiffness matrix, and the matrix of the displacement, and all the applied forces are set to 0. All right. Okay, so this is, you know, K, D, and F is set to 0. Okay. Now this, the next step is to obtain what is called the generalized eigenvalue problem. Right. So now we are getting into eigenvalue problem here. And to obtain the eigenvalue problem, you may recall in solving scalar second order ODE. For the homogeneous scalar second order ODE, let's say without the forcing term, right? So the right hand side will be 0. How do you solve second order ODE? This is a review here, right? It's also in my extra lectures, section 1, section 2 to even section 8. Okay, what's the method to solve not to solve homogeneous? Yeah, so the equivalent terminology here. Free vibration is equivalent to homogeneous, meaning no forcing function. Okay, so scalar linear second order ODE, basically homogeneous, meaning that you need to find homogeneous solutions. So what's your name? Richard, yeah.
You solve, or you find the roots of an auxiliary equation, and then you assume
You assume
the form of the solution, you find the roots of an auxiliary equation.
you find the characteristic equation.
Yeah.
Right? So what form of the solution that you assume, it's very similar to this one. Okay, essentially exponential of lambda x or lambda t. Okay, in the for homogeneous linear second order ODE, maybe let me see what time is it. This, if you are not familiar with this, it's very important. Let me just quickly review here. If you have y double prime, right? Plus a y prime plus b y equal to 0, and y is a function of x or t. Doesn't matter. X is the independent variable and y is the dependent variable. And to solve this homogeneous linear second order ODE with constant coefficients, homogeneous linear second order ODE with constant coefficients, you assume, let's say, for example, e to the lambda x, right? That's called the trial solution. And then you would replace the trial solution into the ODE and obtain what is called the characteristic equation, right? Could someone, let me, Richard, I have already your name on, right? This is, Richard is team 8, right? Can someone quickly point out what's the characteristic equation? Yes.
Isn't it just r squared plus ar plus b?
R, yeah, so, your R is here lambda. Okay,
Okay.
yeah, so be careful. So, yeah, what is your team number?
6.
Team 6, and name?
Dylan.
Dylan, team 6, okay. So Dylan said, if you replace e to the lambda x into this differential equation, you would have lambda square plus a lambda plus b equal to 0. Okay, so please review this, right? It's in my lecture notes, and I have videos also on this. And this is called the characteristic equation. And you see that in the matrix case, it's also very similar. Okay, the method is also very similar. In that, you assume the solution, and the unknown here is the displacement matrix D, right? You assume that the displacement matrix D is an exponential of alpha t. T is the independent variable, and alpha is an unknown constant to be found, just like lambda before. Okay, I could have used lambda in that example. And phi is a constant matrix. Okay, phi is a constant matrix. So, and later on you will see that alpha would be called eigenvalues, and phi would be called eigenvectors. That's the where it's a little more complex than the scalar case. In other words, in the scalar case, you can think of phi as number 1. That's it. Okay. But in the matrix case, you need to have an unknown matrix here, and that matrix will turn out to be an eigenvector. And alpha, the scalar alpha, will be the eigenvalues, and there are 2 eigenvalues and 2 eigenvectors. Okay. So this is clearly more advanced here. And so here is what I wrote. Alpha is a constant which could be real, non-positive number, or a pair of complex conjugate number, with a non-positive real part. But don't worry, it's just like a constant that you need to determine. And phi is the constant. Let me reduce the information here, the amount of information. And phi is a constant column matrix with the same dimension as that of the displacement matrix D, meaning 2 by 1. 2 rows, 1 column. Right? And the reason for alpha to be real number, okay, you can read this later. It's getting deeper, but don't worry too much about these mathematical technicalities. Okay, and follow the development of the thought process for now, and you can come back and think about what is written here. Okay, so that's it. So now what you want to do is to substitute, right, the trial solution. Let me go up here, right? So this is the trial solution. This is what you assume. You substitute into that undamped free vibration equation. Just like in the scalar case, you substitute the trial solution into the ODE to get the characteristic equation, right? So substitute that in there to obtain what? This is what you would obtain. Once you substitute the trial solution into the undamped free vibration, you get this result. Okay, m times alpha square plus k times phi equal to 0. Let's focus on this. This. Remember to give me the signal. Okay, is it already signal? Yes. Okay.
Yes.
So let me finish by showing you why this is obtained like that. Okay, very similar to what we have here. You have D, the matrix of the displacement with D with the underbar is assumed to be E alpha T times the matrix phi, right? So let me write the matrix phi like this. So to distinguish from the uppercase phi, then what would be D double prime, right? D double prime, which is also time dependent, is alpha square. E alpha T times phi, because phi is a constant matrix, so it's not time dependent. Okay, so therefore, if you replace into the undamped free vibration equation, you have mass times D double prime plus K times D vector displacement vector equal to 0. Then you have m mass times alpha square, right, plus K put in common factor, and you have out here exponential of alpha T times the matrix phi equal to the matrix 0. Okay, so now the dimension of 0 here is 2 by 1. The dimension of phi here is 2 by 1. Okay, keep that in mind. Whereas K is 2 by 2 and M is 2 by 2. And so because the exponential function cannot be equal to 0, so you can simplify. Okay, once you simplify the factor exponential of alpha t, you get the result in my lecture notes. Okay, so please collaborate to summarize the lecture. Each team member bring in 1 or 2 points that you learned today. Let me answer.
You have like an equation in matrix form, so like a normal version equation.
Yeah, I guess we're in differential form. You know what I'm saying? Because you can write it like we can write it
Within differential
like this big old thing, or when we split it up, then we have all the shit that affects this force and all the shit that affects that force. You know what I'm saying? Like, I mean, I feel like the only purpose to write a matrix is to write 4 or 5 billion variables in a short. Yeah.
You walk right ahead.
When you said that, you said, nah, you're alright, you walk by.
That was just good talking.